right, this is the 17A video. The topics for this week are going to be light refraction, and Snell's law. So there's an assignment this week. There's a notebook check that's on that assignment, and there is a light activity that's due Friday at 11:59 p.m. No office hours because we're now 5 days a week, and I always put Isaac Newton up there because he did his best work during quarantine. Remember, there are two codes in each video. One is written, the other is a verbal code said by myself. There will each be three numbers, and they are randomly generated, so you cannot guess them. All right, so let's see what we learned last week. So wave. So a wave is a mechanism for transporting energy from one location to another location without transporting matter. So think about waves in the ocean. Then we learned about transverse waves, the wave in which particles in the medium move in direction perpendicular to the direction of the wave that moves. So surface ripples on the water, seismic secondary waves, and then the electromagnetic waves. These are all examples of transverse waves. Now, longitudinal waves is a wave in which particles in the medium move in direction parallel to the direction of the wave. So the examples of that would be like sound waves and the seismic P waves. So they come in different, seismic waves come in different forms of waves. So then we learned about the anatomy of the wave. The crest is the top of the wave, the trough is the bottom of the wave, the amplitude is the distance from the origin to the crest, and the wavelength is the length of one complete wave cycle. Now, compression is a point in a longitudinal wave where the density is the greatest. A rarefaction is a point in a longitudinal wave where the density is the least. So let's talk about measuring the timing waves. So frequency is the number of waves that pass a fixed point in a given amount of time. The unit is 1 divided by seconds, or the hertz. So it's how many cycles per second. The wave period is the time it takes to complete one cycle. It is measured in seconds. So frequency and period are inverts of each other. So the example that I like to use is a hummingbird flapping its wings. So if a hummingbird flaps its wings back and forth 50 times each second, well, the frequency is going to be 50 hertz, 50 cycles per second. Now, the time it takes for that bird to flap its wings once is going to be 0.02 seconds. All right, so then we talk about wave speed. It's the distance a wave travels in a given amount of time. Wave speed depends on the medium. Right, the unit for the wave speed is meters per second. So if we look at the wave equation, we know the variable v is the velocity of the wave. The variable f is the frequency of the wave, and is measured in hertz. The variable, the lambda, is the wavelength of the wave, and it is measured in meters. So when changing mediums, the wave speed changes. The wavelength will change. The frequency remains the same. Right? Just think about if you're inhaling helium. All right, so those are the links for that day. Now, then we talked about sound. And sound is a mechanism or a mechanical wave in which the energy is being transferred from particle to particle interaction. Sound is a differences in pressure. So that's really all we learned that day. But that is what sound is. It's just pressure waves being passed throughout the air. All right. So now the different things that can happen with waves are the wave interference. So constructive interference occurs when two crests meet. Destructive interference occurs when a crest meets a trough. So beats are when two sound waves or different frequencies approach your ear. The Doppler effect is an increase or decrease in the frequency of sound, light, or other waves as the source or observer moves toward or away from the object. This effect causes a sudden change in pitch. So you probably experience this as like a passing siren. So as it's moving toward you, it's compressing those waves because it's moving into that sound source. And you're going to hear a higher pitch. Now, as it's moving away from those sound waves. It's going to stretch those waves out, and you're going to hear a lower pitch. All right. Then, if you happen to move fast or faster than the speed of sound, you're going to experience a sonic boom, which is a shock wave that is produced by an aircraft or other object flying at a speed equal to or exceeding the speed of sound. So it's sort of like a clack of thunder. So the first human-made sonic boom was the bullwhip. So now the reflection is when a portion of the sound wave bounces and returns and a portion of the wave undergoes transmission across the boundary. Echoes and reverberations are examples. Now, refraction of waves involves a change in direction of waves as they pass from one medium to another. So it's a bending path of the waves and it's accompanied by a change in speed, direction, and wavelength of the wave. So this mostly happens when we talk about light, but this is what happens at night. So even cooler and warmer air affect how fast sound waves travel. So at night, those warmer waves are up top, or those warmer air is up top, and it travels faster, so it sort of arcs back down. So that's why it's easier to hear at night than it is at day. So natural resonant frequency. The natural frequency of an object is the frequency or frequencies at which an object tends to vibrate when it is hit, struck, plucked, or strummed, or somehow disturbed. Now, a resonant frequency is a frequency that causes resonance. So think about swinging on a swing. Like you want to push that person on the swing at the optimum moment to get it to resonate. If not, it's not that you're not going to get that whoever you're pushing as high on the swing as you possibly can. So yeah, the usual natural frequencies and resonance frequencies are the same. Then harmonics is an overtone accompanied by the fundamental tone at a fixed interval produced by vibration of a string, column of air, etc. It's an exact fraction of its length. All right, so harmonics are a little bit different. We didn't go over that too much, but it's just a fraction of that wavelength. Now, a standing wave is a vibration of a system in which some particular points remain fixed while others between them vibrate with a maximum amplitude. Nodes are fixed, antinodes are the maximum points. You can see here we have nodes and antinodes on a standing wave. So those are the links for the day, and this is the 17A written code. I would recommend you write that down somewhere. So what are we learning about this? We're learning about light, refraction, and Snell's law. So these are 3 videos. I would recommend watching this. They're pretty good. At this time, I'll give you the verbal code. It is 682. I say that again. The verbal code is 682. And then we're going to be doing 3 experiments: a double slit experiment, Snell you later, the Prism challenge. And once again, those are the links for the day. And I'll leave you with this final thought. As always, there is too much unknown in the universe to take a break from learning. Get out there and question everything.